In this lesson, we'll continue looking at those same sorts of things we were looking at in our last lesson. Last lesson, we're looking at sp3 hybridized orbitals in bonding. Well, now we're going to move from sp3 hybridized bonding, which produces only single bonds and lone pairs, to double bonds and triple bonds, where our hybridization is going to be sp or sp2. All right, so for your homework, you had to do the last of the sp3 hybrid molecules that we're going to do. For homework, you were asked to do ammonia, and what you should have in your notes is not just this formula, but you also want to have a Lewis dot formula. So you start with the electron dot formula, then a sharing arrangement, and then finally the Lewis dot formula. That's how I teach you guys to get to the shape of the molecule. You should also have drawings that show the orbital notation drawings for the nitrogen to show how nitrogen goes from unhybridized nitrogen to hybridized nitrogen. It's hybridizing to sp3. So all four valence orbitals are going to hybridize, combine together to make an sp3 hybrid orbital. And then you should have a drawing in your notes that shows the unhybridized set of orbitals for nitrogen, and then what the hybridized set of orbitals for nitrogen looks like. And I would, well, we've been doing that a lot. If you've got that down, that's not so critical if you know how to do it, okay? My fear is that if you're not practicing that, then you're going to get to the test or something and you can't do it. So the more you practice, the better you're going to be at it, okay? So it's best if you have in your notes the drawing of the unhybridized orbital, showing how it hybridizes, then showing how it forms a molecule, and so that you've got 3 sigma bonds and 1 unhybridized orbital that remains as the lone pair shape for ammonia. And so I'm not going to do that for you because that's what you should be doing on your own. If you want me to look at your work, bring it to me, let me see it. Okay, if you're pretty sure about it, great. All right, but you need to take some responsibility for what you know, and if you need help with it, let me know. I'll be glad to help you. More than happy to help you, but I don't want to show it on here today because I want you to do it on your own. If you haven't done it yet, you still need to do that. Okay, that's something you need to be able to do for me on tests, on quizzes, for homework, to be able to do that sort of thing. All right. So today we're going to go from all these molecules we've been doing that had single bonds to doing some molecules that have double bonds. I've already shown you drawings of double bonds, okay? So what I'm going to do is give you a molecule. I want to ask you guys then to do all those things, right? Electron dot formulas, sharing arrangement, Lewis dot formula. I will give you which atoms I want you to write hybridization for using orbital notation, draw out the molecule, and finally make your molecule, okay? So we don't want to take too much time with this because we're going to try to get 2 molecules done during the class period and have 1 more for homework and probably be done with balloon models for today, okay? So what I want you to do is what's called formaldehyde. And we've worked with this before. We've talked about it before. Formaldehyde is sort of the common name for it. If you're in a anatomy lab or a biology lab, sometimes you'll see biological specimens stored in some kind of liquid in a jar on the shelf. More than likely, not always, that's stored in formaldehyde. It's a carcinogen, so we don't use it in high school as much as we did at one time. Nowadays they store it in really highly concentrated ethanol, probably as much as anything else. But it is still there. And if you're in a really good biology lab in a college setting or a museum or something, you're probably going to have biological specimens stored in formaldehyde. Now, that is not the way that we're going to learn to name molecules. In the next unit, we're going to learn to name these organic molecules. And for this molecule, the way that you learn, this one's going to be called something else. Let me give you the formula first. This is H2 C capital O. Okay? And when you're learning to name biological molecules or organic molecules, you name them in part for the number of carbon atoms in the molecule. Okay, since this is one carbon atom, the prefix for that is meth, M-E-T-H. Okay, this particular oxygen is bonded to carbon. I want you to figure out how it's bonded in such a way as to make that oxygen on this molecule an aldehyde. That's where we get the formaldehyde from. And so this is, in its formal name, this is called methanal. Okay? So meth is one carbon. Ane means there's only single bonds between carbons. Since I only have one carbon, we still call it ane. And al is the kind of bond it has with the oxygen. I want you guys to figure out what that bond is, okay? So I want you to figure out the electron dot formula, sharing arrangement, Lewis dot formula, then the show me both the hybridization for the carbon and the oxygen, and then that using orbital notation, and then finally show me the shape of the molecule in a drawing, and then you're ready to start building your balloon model. Okay, so I'll let you work on that for a few minutes, and then we'll come back and see how you did. I'll do it for you in the class, and we can take a look at how everybody did. Alright, so what we're going to do is take a look at how these might go together. And so hydrogen has one electron dot. You know that by its position on the periodic table. Carbon has 4 electron dots, and oxygen has 6. These are the valence electrons, those electrons in the highest energy level that are most likely to be involved in covalent bonding. So I can bond the hydrogen one time to something, and you can try this in different ways until you find out the one that works. So sometimes it's a matter of some trial and error. I kind of already know the best direction to go in, so that's why I'm going ahead and putting it down here in the way that it's going to go. This is the only way that's going to get those 4 atoms together. Okay, so that each atom has the number of electrons they want to have. Hydrogen has a full valence level when it has 2 electrons. It has one. It's shared one with a carbon. That's 2. And the carbon now has 8. That's what it wants to have. Most atoms want 8. We call it the octet rule. Oxygen now has 8. It had 6. Now it's sharing 2 more to get 8. And so that's we went from the electron dot formula now to the sharing arrangement by showing how we're circling electrons, the electron dots, to get to the number of electrons each of those atoms wants to have. Finally, we're going to draw the Lewis dot formula, and I need a pair of electrons between the carbon and the hydrogen because that's how many are in there, but between the carbon and the oxygen there's 4 electrons, and so we get this. Now the placement of these 2 hydrogens is it doesn't matter if you have it above and below or up to the side and down below, and the same with these pairs of electrons. You can have it above and below or to the side and the top, okay, as long as it's kind of on the 4 sides. That's the first place you go anyway, okay? And a lot of times you see when this molecule is written this way that these electrons are shifted around so that there's one kind of at this angle and one kind of down here, so they're more or less spread around that atom. But for us on the 4 sides is just fine. Now, so that's the Lewis dot formula, what we call in here the Lewis dot formula for methanal or formaldehyde. Then to show the hybridization then for this carbon atom, let's draw the original unhybridized form for carbon. This is orbital notation. So there's 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. In 2pp we put 1 electron in each box and pair up if we need to. Of course we stop there with carbon. In order to find the correct hybridization here, we're going to keep 1 p orbital unhybridized in order to allow for this double bond. For double bond, you have to have a sigma bond and a pi bond. Sigma bonds are always stemming from hybridized orbitals. Lone pairs are always stemming from hybridized orbitals. In a double bond, you have to have one sigma bond and one pi bond. So one p orbital has to remain unhybridized. So when we hybridize this, we're going to combine all the other orbitals. We're going to hybridize these orbitals right here. Okay, and we're going to leave this last one over here unhybridized. So to show that hybridization the way we do it in this class is we put those three orbitals together. Since we put together an s, a single s orbital, and two of the p orbitals, we're going to call this sp2. It's in the second primary energy level. That's what that coefficient 2 here means. So this is 2 sp2. And that last p orbital over here is unhybridized. So that's in the second level, it's p. Now, when we hybridize, then we take all the electrons available in the valence level and put them in these orbitals one at a time and pair up if we need to. So all four of those electrons are separated into separate orbitals. Okay, and that's the way that we picture, using orbital notation, sp2 hybridization. Now, oxygen is going to work the same way. It has a different number of electrons in its valence level, however. Carbon is located here, oxygen is here. It has two more electrons than the carbon does. So we have this many electrons for oxygen, okay? 1, 2 electrons, 1, 2 electrons in S, 1, 2, 3, 4 electrons in oxygen. So the position of oxygen on the periodic table can help us to figure out how many valence electrons we have and where they're located. So now we have a total of 6 electrons in the valence level. This second primary level is the highest energy level for oxygen, so that's its valence level. The highest energy level is the valence level for us. And so 1s is not going to hybridize. It's a lower energy level. It's not involved in covalent bonding. Again, we want to have a double bond, so one p orbital here, this last p orbital over here, is not going to hybridize. The others are, and so we're going to put them together. We've got 3 hybridized orbitals. That's an sp2 because we took one s and 2 of the p orbitals to hybridize. It's in the second primary energy level, and we're going to have one p orbital that's not hybridized. We're going to take all the electrons in the valence level, these 2 and these 4, and put them in these boxes over here, these orbitals, one at a time, one in each box, and then go back and pair up as necessary. And we end up with that. But we have an sp2 electron for the sigma bond, and we have a p orbital here that's unhybridized for the pi bond, plus we have 2 full sp2 orbitals hybridized to make our lone pairs. So here is, let's put carbon, say, right here, and oxygen, say, right here. Okay, and so carbon is going to have a p orbital that's not hybridized. So that's that double balloon shape. Oxygen is also going to have a p orbital that's not hybridized, as we can see there. All right, and then there are 3 hybridized orbitals that need to be spread around both the carbon and the oxygen as far as they can get, and that means they're going to be, if we call this the polar positions, imagining this is kind of a sphere we're imagining here, so this is North Pole and South Pole here, then everything else is going to be on the equator. Okay, it's going to be kind of in a circle right here on the equator in 120 degree angles, or 120 degree angles apart from each other. So I'm going to have one hybridized orbital that's more or less pointing toward the oxygen so that I can do that sigma bonding. Okay, and that's going to put those other 2 orbitals 120 degrees apart. That brings one of them swinging out sort of toward you here, and one of them that's back behind that more or less. Okay, the same thing over here on the carbon. All right, so this is an unhybridized p orbital. Okay, p x, y, or z. What do we want to call it? X. Okay, px, because it's on the x-axis. Okay. All right, so these then are going to, well, first of all, we need to hybridize. We need to show the sigma bond that's going to exist between the carbon and the oxygen. So these two are going to combine. Okay, there's one electron. This orbital here is one of these three there. There's one electron there. There's one electron here in this oxygen. Let's see, I need to make it go down and not up, so that they have opposite spins. Okay. And then they're going to combine. And then we can also then combine or connect together these p orbitals. So I've got two parts of the p orbitals. They're going to reach out to each other in this fashion. Okay. On the carbon then, I've got two more valence level hybridized orbitals that are available to do hydrogen or bonding to the hydrogens in a sigma bond, because it's a sigma bond by definition is a bond that lies directly on a line between the nuclei of two atoms. So I've got the hydrogens out here. They've got only electrons in the s orbital. Okay, I should have made that a blue one over here instead of that pink to sort of match it up here. And then they're going to connect into a sigma bond here. So both these hydrogens have a single electron. Both these orbitals on the carbon have a single electron. I should have made that going down, so it'll match that going up. Let's fix that so get that kind of straight. Alright, and then the oxygen over here has two hybridized orbitals that are full. Okay, so lone pairs are always going to be hybridized orbitals. So these two have two electrons over here. Okay, and that's sort of how everything is going to go together. So when we put it together then, there's going to be this sigma bond right here. That's that wiener shape. Sigma bond, two electrons in there. There's a pi bond going across the top and bottom. It's one pi bond with two parts. Okay, so this was px. We're going to call this pi x. Okay. Then we've got the two lone pairs over here on the oxygen. We've got the two sigma bonds going out here to hydrogens. And the lone pairs, of course, have two electrons there. That's why we call them lone pairs. Okay, and so that's the shape of our molecule. Does that make sense? All right, now, when you make this molecule, you're going to need two round balloons here. I'm sorry, it's off the screen. Two round balloons here. Okay, you're going to need a long balloon here, but here's the problem. You're going to need to be able to tie a knot between this end of this balloon and these two, and a knot over here as well. So this is that case where you need to have a little part of the balloon at the end. You need to tie a knot in it before you actually do it. So we were doing our bonds last week like this. Now we need a slightly different sort of tying system in order to put together a double bond. So in order to tie this end of the balloon to these others, I need to have a piece of it here that I tie a knot in before I do any blowing of anything up. Okay? Like that. That way I've got something to tie together here. The same is true for this double bond. So the double bond, you're going to blow up a little. This one, you got to get your lengths right here. Okay. Whatever. Remember, we're trying to make sure that this bond is not a great deal longer than these. Okay. But then these need to be 1.5 times longer than this in order to make that curve. All right. So if I'm blowing up this balloon, say 8 inches long, then this one needs to be 12 inches long because it's 1.5 times longer. 12 inches here and 12 inches here. So I can make a little piece on the end on the orange one here. I can make a piece on the end, blow it up 12 inches, tie a knot, blow it up another 12 inches and tie a knot, and now I can make the pi bond to go around this sigma bond. All right? But now these two on the end over here, they can look just like the ones we've been doing from last week. Okay? Everybody understand? All right, let's get started. For our next model, then we're going to do something called hydrogen cyanide. Hydrogen cyanide is a very poisonous gas. Cyanide, the ion, is something that's used as a rat poison. So sodium cyanide is potassium cyanide. Those are potassium cyanide, I think, is the rat poison, what you buy at Lowe's, the rat poison sometimes, or at the hardware store. Hydrogen cyanide is a gas, and so back when they used to execute people with the gas chamber, that's what they'd use is hydrogen cyanide sometimes, okay? And cyanide is just a carbon and a nitrogen, okay? And so hydrogen cyanide is HCN. As long as the gas, it forms a molecule. So you're going to try to figure out electron dot formula, sharing arrangement, Lewis dot formula. I want to see the hybridization on, let's just do the nitrogen, the hybridization of the nitrogen this time, okay? We don't need to do two different atoms necessarily. And then show me the shape of the balloons and, as you draw it out. And if you want it, you need to know how to go through the progression from non-hybridized balloon shapes to hybridized balloon shapes, and then finally get the shape of the molecule itself. And then the key is before the class is over, you want to make this molecule. So if you want to do the other stuff at home, that's fine. Figure out what the shape of the molecule is going to look like for your balloon model before you leave. Okay, so you can get as much of that done as you can. So this is class work. Homework then for tonight is to make a molecule of carbon dioxide. Okay, now this will be a little bit trickier. It's not one that's, it in some ways is a little bit different than what you're used to, but if you just work your way through it, you should be able to figure this one out. Shouldn't be too hard, okay? Any questions about that? If you need help with it, just ask me, okay? You try it tonight and you're like, oh no, I don't know what I'm doing. You can ask me tomorrow. I'll give you an extra day to get it done, but you need to be able to make a molecule of carbon dioxide. Okay? Show the bonds in the molecule using balloons. All right.